How do you fit something the size of a dining table into a box the size of a shoebox, and then unpack it in space, completely blind? The success or failure of a multi-million-dollar space mission can hinge on the single snap of a thread thinner than a guitar string. This is the world of CubeSat deployable mechanisms. These tiny satellites need to unfold big hardware like antennas and solar panels once they reach orbit. The challenge is twofold. How do you reliably release these components on command, and how do you confirm the deployment was successful from millions of miles away? Let's tackle the release first. One of the most common solutions is deceptively simple, the burn wire release mechanism. It consists of a high-resistance wire, typically Nichrome, wrapped around or threaded through a restraining cord made of a strong polymer like Dyneema. This cord is under tension, holding the spring-loaded deployable like a solar panel in its stowed position. It's like a tiny, high-tech leash. When mission control gives the command, a specific current is sent to the Nichrome wire. Its high resistance causes it to heat up instantly. This heat is just enough to melt the polymer cord right at the point of contact. The cord severs and the leash is broken. With the restraint gone, the stored energy in the springs is released, pushing the panel or antenna out to its fully deployed position. Now for the second problem. Did it actually work? We can't see it, so we need sensors to give us a definitive yes or no. The most straightforward sensor is the humble limit switch. It's a simple mechanical button placed at the end of the deployable's travel path. As the solar panel swings open, it physically presses this switch at the very end of its movement, just like flipping a light switch. This action closes an electrical circuit, changing a voltage from low to high. The satellite's computer reads this change as a successful deployment. This provides unambiguous confirmation. The data is then sent back to Earth, turning that unknown status to a satisfying deployed. But what if you want more redundancy or need to avoid physical contact? That's where non-contact sensors like Hall effect sensors come in. A small magnet is attached to the moving part, and the sensor is on the stationary frame. The sensor measures the strength of the magnetic field. When the panel is fully deployed, the magnet is right next to the sensor. This specific magnetic field reading tells the computer its exact position. Another clever non-contact method uses light. An optical sensor consists of a small LED light source and a photodetector. In the stowed position, a small tab on the deployable blocks the light beam. When it deploys, the tab moves and the light can finally reach the detector. This change from dark to light is an unmistakable signal. It's a simple but incredibly robust way to verify deployment. Often engineers will use multiple sensors for redundancy. For instance, a limit switch for primary confirmation and a Hall effect sensor as a backup. This layered approach ensures that even if one sensor fails, mission control can still be confident that the hardware is in its correct configuration. So let's put it all together. A command from Earth triggers a current. The burn wire heats up, severing the restraining cord. The spring-loaded mechanism deploys the solar panel. At the end of its travel, it triggers a sensor, confirming the action was a success. This entire chain of events, from release to sensing, happens autonomously hundreds of miles above our heads, often in just a few seconds. Burn wires and deployment sensors are the unsung heroes of the small satellite revolution. They're simple, reliable, and absolutely mission-critical. They transform a CubeSat from a dormant box into a fully operational scientific instrument, ready to perform its mission. From monitoring weather patterns and providing global internet to studying distant stars, these tiny mechanisms enable giant discoveries. If you enjoyed this look into space hardware, be sure to subscribe and hit the bell for more deep dives into the engineering that powers exploration.